All right, so we're going to practice graphing a little bit more, and I'm going to show you some other graphs. And let's start by doing tangent. We didn't do tangent. We did sine, we did cosine last time. Let's do tangent. Okay, now tangent, as you saw from the application, that little animation I showed you, okay, it's got a weird S curvy shape going on. But the box method is still the same. That's going to be universally true for all of the 6 standard trig functions: sine, cosine, tangent, secant, cosecant, cotangent. There's really no difference between any of them. Okay, so let's make an example. Y equals, let's just start off with something simple. Let's just do tangent of x without any parts on it, because fooling around with okay, once you the box, there's really nothing more exciting going on. Okay, so let's start off, and we have our axis. Now, this was a piece of advice. Oh, did I not give you paper? Oh, I'm sorry. Yeah, go ahead. This was something that I saw and a couple people had issue with. And if it's you guys, I'm going to go ahead and introduce a phase shift just so that I can found an issue that some of you guys have. The question was, like, what do I do with my y-axis? I wrote it down, and then my phase. So here's my advice. Start off, and let's put in tangent of x minus pi over 3. Okay. Now, we need a vertical axis in order to say where our phase shift is, what our amplitude is. We need that. But my advice is, don't put a vertical axis through 0. Create a vertical axis and draw it really lightly, because you'll erase it. It's a neat trick. So, let's first, pi over 3. Guess what? There's pi over 3 right there. Now, I need a vertical axis, so I'm going to make one. I'm going to have an amplitude and a baseline of 0. So I'm just going to go up and down 1. And as far as I'm concerned, 1. But I want to make it symmetric about the axis, so I'll use a compass or, use the ruler, whatever. Oops. If you want a compass, they're on my desk. You're welcome to grab one. All right. Now, what is my B term, which is the frequency? 1. It's not written. We take it as 1. So that means that we have to determine the width of this wave first. So the period is equal to 2 pi all over 1, which was the B term. So that means that the width wave is 2 pi. So we start at pi over 3, and we add 2 pi to it to find the other end of the box. All right, so that's where the box begins. And now I just add 2 pi. So 2 pi plus pi over 3 gives me what? So, yeah, pi over 3 plus 2 pi. And I'm going to erase this in a minute, but all right. So that's the quick and easy calculation, add, subtract fractions. So I'm going to say that is pi over 3. All right. I don't really care. Get big and wide and as big as you'd like. All right. Now we have to find roughly called quartiles. Break this apart. So we have, and if it's okay, I'm just going to go shrink this guy. Guess what? He dies. All right. So average of 7 pi over 3 and pi over 3 becomes 8 pi over 3, which is 4 pi over 3. Now, this transversal is there just for graphing purposes. It is not part of the graph, nor is it part of the graph. And the average of pi over 3 and 4 pi over 3, 5 pi over 6. Right? Pi over 3 and 7 pi over 3. Over 6. Okay. So there's the box. Okay. Great. Everybody got it graphed? Okay. All right. But if you think about tangent, and we think about the unit circle, and as we spin around the unit circle, tangent becomes undefined at certain places. When does that happen? At what and what? Okay. But if we think about the unit circle, just for a minute, hop off mental image. Remember, we're all about the mental picture rather than memorizing, right? Okay. We start off, we go 1/4 of a whole circle, okay? And that's where it's undefined. And then it's okay, it's okay, it's okay, and then it's undefined at 3/4. So if we think about the box, it's kind of a circle that's kind of been rolled around through the box, okay? Take that self. If I take a unit circle, something like that, and if we say, off to the side, let's do this. There's 0, there's 1/4, there's 3/4, a little smaller there. The idea is that it wheel through the box. It's kind of lousy to do. Really lousy stop animation. This is probably a very funny bit of the video. I hope someone's laughing. I am for you. At that first quarter, that's where I get an undefined. Okay? And then as I keep rolling, nope. I get my other undefined at the 3/4 mark. See? So it's the first quarter and the third quarter that I'm undefined at, and that's where I draw my asymptotes. I was close. Good. So I am undefined at those two places. I want to be a little thinner, and I'll use a pretty color. That's where I'm undefined. Okay? All right. Now, if it's okay, I'm going to try and zoom out a little bit here. Okay. We're good. We have our box. We have our asymptotes. Now all we got to do is graph it. Now, tangent is a little bit weird. All right? But we start off climbing because as tangent rolls in its circle, it gets bigger and bigger and bigger and bigger until it gets to that asymptote, and then boom, it's undefined. And the second you go past pi over 2, now your slope is negative. So you fly all the way down to negative. You go from positive infinity to negative infinity, get a case of whiplash, and then start climbing back up. Okay. And finally, as soon as you pass over 3 pi over 2, boom, all of a sudden, instantly again, you have a negative slope. Okay, now, I've seen all kinds of abominations when it comes to what a tangent wave looks like. Here's a good guiding principle. Because some people, they'll give me stuff that does this. Excuse me. I'll see this. And I'm like, no, not really. In fact, the guiding principle is that right here, where it crosses through the box, is the midpoint of that interval. Okay? So if you can make your tangent wave go through that midpoint, that will give you an idea about how fast it's climbing. Okay? And the same thing goes on in here. It's supposed to go to that point, and that point, and that point. You don't have to draw those, but that's just, if you want to, you're fine, that's cool. But that's a way for you to see just how fast it whips up there. All right? Does that make sense? See what points I'm talking about? Cool? Awesome. Okay. Since we're here, I'm going to show you what cotangent looks like. Okay? Cotangent looks remarkably similar. Actually, I'm going to go ahead and just clone the page. There you go. Wait, hold on. I want to make sure I've got my yeah. That's it. Sorry. That's it. There's your cotangent. Okay, so tangent and cotangent look very much alike. take a second, draw it, make sure you're all good. The first time. Yeah, I know, you hate me. It is that one. Because remember, at zero, it all looks the same anyway. Um, think about tangent at zero. What is the tangent of zero? So what is 1 over the tangent of zero? Undefined. That's why a mathematician's favorite tool is an eraser. So you did it in pen. Oh, that sucks. Mm-hmm. Where tangent was 0, cotangent is infinite. Come on. Where are you? Fluffy. What's going on here, buddy? Sorry for those of you who are watching this recording. There you are. Thank you. Okay, so tangent is faint. It's very faint right here. Okay? So you can see the tangent and the cotangent together. And, I mean, they're not perfectly aligned, but you can see that when one is infinite, the other one is undefined. And they are equal at pi over, if you think about the circle, when you hit pi over 4, the slope is 1, the reciprocal of 1 is 1. So that's why the cotangent and the tangent intersect each other at a certain point, because the reciprocals are the same at that point. You see down here, right here, you see that? At that point, you have the unit circle would be going through pi over 4, right? Does that make sense? The reciprocal of 1 is 1. And then here, the reciprocal of -1 is still -1. So that's why the cotangent and the tangent intersect. Right? That fly? Okay, good. Okay. Okay. Now that I've thoroughly confused all of you. Yes. Because at this point, right there, okay, in tangent, that point, I hit the vertical, at the quarter mark, at pi over 2, right? Yeah, as I roll through that circle, the first place I hit where I'm vertical is the first quarter. What's that? And yeah, when it's cotangent, it would be 0 over 1, right? Because remember that sine, and I'm not even, this is where we're going next, but tangent is equal to sine over cosine. Have we talked about this yet? And this is where we're going to be going in the next couple of classes from now. Think about a right triangle whether it's on a unit circle or not. This is sine, and this is cosine. Okay? If it wasn't a unit circle, it's just scaled up, r, the radius times sine or the radius times the cosine. Well, the tangent is rise over run. It's the slope. So tangent is sine all over cosine. So when you're thinking about the tangent is undefined at pi over 2, because at pi over 2, the sine is 0. And then when I do the reciprocal of tangent, cotangent, that's cosine over sine. And at pi over 2, cosine is 0 and sine is 1, so it's 0 over 1, which is 0. Okay? Once we're done with graphing, we're going to this is the idea as to why some things are undefined in some places and why things are 0. Okay? All right. Now, secant, cosecant are very much alike. Again, mostly because sine and cosine are so much alike. So, let's do one of those. Before we even go there, the phase shift was an issue here, right? The question is now, where the heck do you put your axes? Yeah? Well, we are at pi over 3. We've shifted everything over like that. So now the question becomes, where the heck do we put our axis? Okay. Well, one easy way to do it is to say, all right, how many of these waves do I have to go to hit? So if we look at this width, that width right there is a full pi, isn't it? Because we go from pi over 3 to 4 pi over 3. So that's a full width of 1 pi. Took it away. So I went backward. We have pi minus pi over 3. Okay? For pi over 3 minus pi. So we would be at negative 2 pi over 3. Okay? So you would 0. Past 0. Now we say to ourselves, okay, this width is the width that matters. I just need would be that interval. So if the interval starts at negative 2 pi over 3 and ends at 1 pi over 3, 0 would be how? Through? Third of the way through? 2/3 of the way through. That's where 0 goes. Yes? Another way to look at it is to say, all right, plug in 0, what do you get? Well, at 0, I have the cotangent of negative pi over 3. Yuck. And then, well, we'll get there in a second. Let's actually, well, for giggles, we'll do it. Well, this is the same thing as if I add 2 pi, I end up with what? Negative pi over 3 plus 2 pi? right? Pi, or add 360s however many times I need to, right? So this is the same thing as 1 all over the tangent of 5 pi over 3. What is the tangent of 5 pi over 3? What's the tangent of 5 pi over 3? I'm doing this. Okay. See him, he's sweating. I think he started to shake. There might be a tear coming. Theft! Sorry. What do you got? Theft. What do you got? Negative radical 3. Right. So this is 1 all over negative radical 3, which becomes negative square root of 3 all over 3, which is a small negative value. And if we think about that, that's about what it would look like. Okay? It wouldn't exactly go through it because that width isn't enough. It would actually go through the axis before it hit. It would go through the y-axis at a small negative value before it hit the x-axis. Okay? Practice. It'll take practice. And remember, you're never wait a second. I think you were talking about this page? Okay. The only reason why we learn it is so that we can understand how the wave is built and we understand what cyclical and periodic waves are like. Because what we're going to be doing next and what your homework assignment is going to be is I'm going to give you real life things and you're going to have to make a wave that fits it. Okay? You know, like the classic Ferris wheel, that kind of thing. And we're going to do the Ferris wheel example in a minute. All right, so secant, cosecant, cotangent. So secant of theta. It's the inverse of cosine. You know what? The history of trigonometry is actually really kind of cool. Like, why is it called sine? Where did the word come from? Where did cosine? Why do we call it tangent? What is it tangent to? And then there are other old ones that no one uses anymore called the versine and the vercosine. Yeah, they're really cool. Yeah, but it all comes down to the unit circle. And if you do a little bit of homework on it, it's really kind of neat. And in fact, it's the kind of thing like, you know, trigonometry on a sphere is totally different.
Doing it actually on the ground.
I mean, if you think about looking up at the celestial sphere, imagine doing imagine a triangle painted onto a circle. All of a sudden, the Pythagorean theorem doesn't hold. Yeah, all sorts of crazy stuff happens. And if you're interested in that, that's a fantastic IA. Anyway, so I'm going to go ahead and just quickly run through this. because I kind of want to get moving on this one. All right. When you decide to graph a secant, that cosine wave needs to be drawn really, really lightly, or not at all, because it's only there as a guide. Okay, I'm not asking you to graph the cosine. I am asking you to graph the secant. Okay, and I'm going to go ahead and give myself. Okay. Mm. Okay. Give everybody a second to draw that. Now, that was 1 second. That was quick. So now, just like cotangent and tangent, wherever one of them is 0, the other one is undefined. So every time this wave crosses through the x-axis, I get an asymptote. Okay. And if you remember a minute ago, I said that the cotangent and the tangent, they intersected at the top of the box, right? They intersected at 1, at the maxima, right? Or, when the reciprocal was itself, they intersected. So whenever somebody is at 1 or -1, their reciprocals will be 1 or -1. So secant and cosecant intersect sine and cosine when they both have a value of 1. And in this case, I am at a value of 1 right there. At that point, cosine, which is the green wave, is at 1, the cosine of that point, whatever value that is. In fact, that's 2 pi, is 1. So that means that I am touching the green dot, the green wave, at the red dot, and I am asymptotic at those vertical lines. Okay? So that means this guy looks like this. And that's a little too faint. And that is secant. So take a minute and graph it. I'm a little bit sloppy there. A little better. And in fact, it's quite pretty, I think. Now, obviously, since sine and cosine are very much related and look basically the same, but one of them has a phase shift, you do the exact same process for cosecant, except you would start with a sine wave. So I'm going to pause the video. Just you can maybe take a look and see where everything's going. Pause for a commercial break. All right, so it's a classic problem. There's some, the Ferris wheel model problem is the kind of thing that is done in every calculus course. All right, you're riding a Ferris wheel. It's always good to draw a picture. There's my Ferris wheel. There we go. My distance from the ground varies sinusoidally with time. When the last seat is filled and the Ferris wheel starts, your seat is in the position shown. That's where you are. Okay? At time 0, that's where you are. Okay? So time is the variable in question. As time proceeds, I oscillate. You find that it takes you 3 seconds to reach the top. Please. Yeah, compasses are in the green box if anybody wants one. 43 above, at the top, you are 43 feet above the ground. .43 feet. Okay? And the wheel makes a revolution once every 8 seconds. Okay? The diameter of the wheel is 40 feet. What? Did I say 8 or 3? Oh, I'm sorry, it is 8. Sorry. So the diameter of the wheel is 40 feet. That tells me some things immediately. How big is the radius? 20 feet. How high is the wheel above the ground? 3 feet. So any small children had better watch out. The diameter was 40, and so the radius is 20. Okay. Now, how do you do this? First of all, we have to begin thinking about what our variables A, B, C, and D are in the equation here, okay? So, this one begins by asking us to sketch a graph of this sinusoid. Okay. First, what is my amplitude? 20, right? from the top to the bottom is a total of 40. So I go up 20 and then I go down 20, and then I go up 20 and I go down 20. If we think about the midline being when you are horizontal, and then you go up to a maximum of 20, and then you go down to a minimum of 20 below, right? But, okay, so now we have to say, what is, if my amplitude, and actually we can start by actually doing this right away. Not theta, but t. All right, so first of all, we know what A is. A is 20. What would D be? If it was 3, which is a reasonable thing to start with, that means that I would go up maximum of 23 and then go plummeting 17 feet underground. And then to 3. What do you mean? Where is the midline of this wave? How high above the ground? 23 feet above the ground. Here's why. That's why. Because the lowest my wave is going to go is 3 feet. The highest is. So I need to be. Okay. Okay. Now, if it takes me 8 seconds to go a full cycle, what does that represent? Period. Okay. So, the width of a wave is going to be 8 seconds. Okay? That is 8 seconds. What should I call the beginning of my box? Where should I put at the beginning of my box? What is this x value? Or in this case, t value, the beginning of a wave? Well, at time 0, I started off at this oddball angle. Remember, a wave is a single crest. Sorry, is a single cycle. So crest to crest or trough to trough. As long as I go from one place to the next place, to an identical place, then I've gone a complete wave, right? So I would say let's start our wave at either a maximum or a minimum or a 0, which are easy to graph. We're given 3, and we start at a maximum. And then 8 seconds later, we're back again where we wanted to be. So this would be 11. Okay? I'm sorry? At 11, I'm at my maximum height again. And then at 19, I would be at my maximum height again. 27, and blah, 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 blah. Yeah, sorry, 26. So. All right, so at 3, I'm at a maximum. At 11, I'm at a maximum. Wait a minute, there's something goofy with my wave. What trig function starts at a maximum? Cosine, which means I don't want sine, I want cosine. Okay? I could then with sine built the wave. Okay? Okay. Now, we're running low. Okay. Now, let's put all of our things in place. Eyeball that. And draw the wave. Okay. Now, let's find my B and my C. First of all, let's go for C. What do you think C should be? How much do I offset this wave before I begin it? 3 seconds, right? Like we kind of like let the wave go for 3 seconds before we start dealing with it. So what should I put right here? -3, right? Because we're shifting it to the left, to the right. And now we got to futz around with B. Remember, B is the term that 2 pi is divided by. It's the width of a wave. I'm sorry, the number of cycles in 2 pi. So the period in this example is what? What's the width? The period is the width of a wave. 8. So this becomes hmm? Okay. By the way, notice that in all of the examples we've always had before, the B term was like 2 or 5 or 7 or something like that, right? They didn't have pi in the B term, did it? Like in all the graphs that you've ever seen, it didn't really ever kind of make sense to have a number B, like a whole number or something like that. Here, now all of a sudden B has a pi in it. Okay? That's important. Real life things don't worry about pi. Okay? Pi is a number that is a mathematical fabrication based upon the principles of a circle. Okay? The world does not run in terms of pi. It runs in terms of counting numbers. Okay? So when you're dealing with a real world example, very, very often we have a B term with a pi in it so that the pi's cancel out and we then have seconds or minutes or days or years rather than having some irrational number. Okay? So real world examples often have a pi in the B term. So of this wave would be, or a equation of this wave would be, okay? All right. Next, we have to fool around with shifting this thing so that it becomes a sine wave or something like that, okay? Now, the phase shift between a sine and a cosine wave is how much? 90 degrees or pi over 4. So, sorry, pi over 2, excuse me, thank you. So what I need to do is I need to figure out how to shift this guy a quarter of a wave. Okay? We'll pick up this next class. I'll post a homework assignment. It'll be due in 2 classes, and we'll deal with this next class. Okay? This episode of the Ronco Show has been brought to you by Ferris wheels, sine waves, and Rayleigh scattering.